Hey Chem 240, this is Dr. Ricardo. We're going to be doing the second video of chapter 15. There's going to be 3 videos in total. So this starts off on page 10 of my notes, and we're going to discuss what to do when you have a homogeneous equilibrium and what you do when you have a heterogeneous equilibrium. So the definition of a homogeneous equilibrium is an equilibrium that involves reactants and products in a single phase. So typically, it's going to be everything in the gas phase or everything in the aqueous phase. Those are going to be the typical versions of homogeneous solutions. Heterogeneous solutions have something that's not in one of those phases. So let's say you have most of the chemical reactants and the products are in the aqueous phase, but you have a solid or a gas. Then you would leave those things out, okay? The other thing that you're going to leave out is liquid water, and we'll talk about that in a reason. Okay, so let's read the definition of a heterogeneous equilibrium. Heterogeneous equilibrium is an equilibrium that involves reactants and products in more than one phase. So an example of that is if you had a chemical reaction like the one down here, where you had iron solid reacting with water gas to make iron oxide solid, this is rust, plus hydrogen. So 2 of the things are in the gas phase and 2 of the things are in the solid phase. So this equilibrium down here would be considered a heterogeneous equilibrium. Okay? Now, this is a really important note. Whenever you write the equilibrium constant equation, the capital KC, right? You are going to do the following. You need to omit the concentrations of any pure solids and liquids, okay? So everything is going to be of interest to you is going to be either in the gas phase or going to be in the aqueous phase, okay? So I'm going to give you 2 examples of that, including liquid water in an aqueous phase reaction, okay? So let me read that one more time. Omit the concentrations of pure solids and liquids, including liquid water, from the equilibrium constant expression because their values don't change very much. So if we're going to write the equilibrium constant expression for this balanced equilibrium reaction, so just double check that it's balanced. There's 3 irons, iron times 3. There are 8 total hydrogens. There are no hydrogens over here. 4 times 2, there's 8 total hydrogens. And what about the oxygen? There are 4 oxygens here, and all the oxygens wind up in the iron oxide, so there's 4 over there. Okay? We're telling you that you can establish this reaction and get it to come to some kind of equilibrium. Okay? This is a gas phase equilibrium with 2 solids present in the equilibrium mixture. Okay? So if I was going to write the C for this, the equilibrium constant in terms of concentration, what I should do is write down the products divided by the reactants, where the coefficients become the exponents. So remember, for equilibrium constants, it's very simple. If you have the equilibrium constant expression, it's products divided by reactants. The coefficients become the exponents. Okay? So, and last thing, leave any solids and liquid water out. So let's take a look at this. When I look at the products, the only product that I have that's a gas is hydrogen, right? So this is a gas phase equilibrium. So I need the concentration of any gas phase products. So that's hydrogen. Why is it raised to the 4th power? Because this coefficient is 4. Okay? So the coefficients become the exponent. Divided by any gas phase reactants. Well, water, vapor, right? Gaseous water is the only reactant that is a gas, and its exponent is going to be to the 4th power because its coefficient is 4. So I leave out the iron and I leave out the iron oxide because they're solids. Now, interestingly enough, you have the numerator to the 4th power divided by the denominator to the 4th power. That's the same as the whole thing to the 4th power. So you can write it either way. Usually we're just going to write it this first way. So the equilibrium constant in terms of concentration, the C is for concentration, is products over reactants, coefficients become the exponents. Here's a second example. Okay? And the second example is an aqueous phase equilibrium. So we have a weak acid, HA. Okay, don't worry about what A is. It's just the rest of the molecule after the H ionizes. So HA aqueous reacts with liquid water, okay, donates a proton to the liquid water to make the hydronium ion, H3O plus. I'll make the plus a little bit better. And A minus, which is the conjugate of base of HA, and we're going to learn that again, or review that again later on. So after this H plus comes off, winds up on the water, what's left? A minus. Okay, so if I give you this and I say write the equilibrium constant expression, products over reactants, coefficients become the exponent, leave solids and liquid water out. Okay, so we have these two things are the products. They're both to the first power because their coefficients are 1. We only have one thing in the denominator, the HA, right? I'm leaving the liquid water out. I drew it over here for a second and then crossed it out to show you why it makes sense to leave it out, okay? If I calculate how much water is in pure water, okay, it's an incredibly large number. So let's do that calculation. What is the molarity of pure water? Well, molarity means moles of solute, moles of whatever it is that you're interested in per liter of solution. So let's assume we have 1 liter of water and ask ourselves how many moles are in 1 liter of pure liquid water. Okay, well, in 1 liter of water, 1 liter of water has a density of 1 gram per milliliter. So a liter of water has a mass of 1,000 grams. If I have 1,000 grams of water, how many moles is that? Well, I divide by water's molar mass. So 1,000 divided by 18 gives me 55 moles of water in 1 liter of water. Well, if I have 55 moles of water in 1 liter of water, that makes the solution 55 molar. So all I would be doing in my Ka expression, what's the A for? Is this happens to be the equilibrium constant expression for an acid. But it's still a Kc. It's the equilibrium constant in terms of concentration. Why? Because I have my brackets. Okay? This is just a specialized version. Remember, these K's are capital, right? Very important. Not rate constants, equilibrium constants. Well, why would I constantly have this number 55 in the denominator, right? It's basically a constant because these numbers, the amount of HA is going to be on the order. How much acid can actually dissolve in the water? I mean, at maximum, it's something like 1 molar, but in reality, it's usually like 0.1 or 0.2 or 0.01. These are tiny, tiny amounts of acid in the water. So if this equilibrium occurs, no matter where you are on the equilibrium, this number is 55 compared to 0.1. So even if I use up all of the acid and it goes all the way to the right, this number is going to be 54.99 something. So it's hardly ever going to even move, right? So no matter which way this equilibrium is going to go, adding a little bit of water or taking a little bit of water out isn't going to make any difference whatsoever. Okay, so we just leave it out. We don't want to drag around that 55 molar wherever we go. Okay, so since it's always 55, we're going to omit it. If we left it in, what would happen is your Kas, or whatever kind of K you were dealing with, would always just be 55 times less. Okay? But again, the convention is to leave it out because it hardly changes. So I'm crossing it out, cover it with my finger. That's what you're going to be working with. Products over reactants, coefficients become the exponent, leave out solids and liquid water, right? Because it's the solvent. There's so much of it around. Okay, second page. This is page 11 of the notes. How do we predict the direction of the reaction? In other words, just by looking at the size of the equilibrium constant, we can get an idea as to which is favored. Are the reactants favored or are the products favored? So by merely looking at the magnitude of Kc, you can tell whether the reaction favors products or reactants. Okay, so if I have a very simple equilibrium of A gas going to B gas, okay, if I start with some A, and allow it to come to equilibrium from this side, or if I start with some B and allow it to come to equilibrium, once it comes to equilibrium, then we know that Kc is going to be the products over the reactants, coefficients become the exponents. So I just have concentration of B over concentration of A. So if Kc is a very large number greater than 1, right, something like 10, 100, 1,000, it means that B is in much greater concentration at equilibrium than A. So if Kc is greater than 1, you're going to favor the products. Now, what do I mean by favor? That once it comes to equilibrium, there's going to be a lot more molecules of B around than A. Okay? What happens if the equilibrium constant is much, much smaller than 1, right? This situation up here, less than 1. Well, that's going to favor the reactants, which are A. Why? Because the only way I can get a number much less than 1, something like 0.1 or 0.01, is that the denominator swamps the numerator. There's much more over here than there is over here. Okay? And what happens if it's equal to 1 or right around 1? Well, if it's equal to 1, the concentration of B and the concentration of A just happen to be the same. So whatever they are, they've got to be the same. Okay, so if it's something like 1.1, then B just beats out A by a teeny tiny amount. So it doesn't matter what you start with, right? I can take some A, throw it into the beaker. It's going to come to this same equilibrium. I can take some B, throw it into the beaker. It's going to come to that same equilibrium. I could take a little bit of A and B, mix them together. It's still got to work itself out until the B divided by the A is whatever the number the equilibrium constant is. The equilibrium constant is only going to be a function of temperature. Okay, so how do we quantify this idea that we might want to compare the initial concentrations with the equilibrium concentrations? Well, we're going to do that with a new thing called QC. QC works exactly the same as Kc, only instead of talking about equilibrium concentrations, you're going to be talking about what you put into the vial to start with. And then we're going to compare where you start with, right, the number you have at the beginning, whatever the scientists choose to throw into the beaker, with what the equilibrium value is, and we can get an idea, how are we going to approach equilibrium? Are we going to approach equilibrium from the left-hand side because we overdid it and have too much A and B around, okay, and it's got to go to the right-hand side to come to equilibrium? Or if we just put C around, or some C and B, are we going to approach equilibrium from the right going to the left, right? It's got to get to this equilibrium, this double arrow, where the concentration values don't change because the rate of the forward reaction is going to be equal to the rate of the back reaction. You come to this, what seems like a stagnant state. The concentrations don't change. Do we get there from this side, or do we get there from this side? Or do we just happen to be so lucky that we put exactly the right amount of stuff in the beginning that we're already at equilibrium, which is really hard to do. It's hard to weigh it out so it gets exactly to equilibrium. Okay, so how do we determine QC? Q, okay, is called the reaction quotient. C means in terms of concentration. We're going to use parentheses instead of brackets. So parentheses are going to be still moles per liter, but not necessarily at equilibrium, but you could even put little zeros here, right? They're the initial concentrations, okay? But still works. The products divided by the reactants, the coefficients become the exponents. So this guy has a 2, the A and the B have 1s, okay? So what's the difference between this and this? This is the given concentration. This is the concentration that the scientist puts in, or you put in lab. And what is these guys over here? These are once it comes to equilibrium, okay? So two things are going to happen. Well, three things could happen. They could turn out to accidentally be equal, and then we would already be at equilibrium, right? If I put in just the correct percentages that this number here is equal to this number here, I must have hit it just right. I must be at equilibrium. But that's usually not going to happen. Usually, you're going to put stuff into there, you're going to throw some A in, you're going to throw some B in, and you're going to throw some C in. And then you're going to say, am I over here? Do I have too much reactants and it has to go to the right? Or am I over here? I have too much product and it has to go to the left. So first scenario, if QC is greater than, if KC is greater than QC, okay? Or another way to say it, if QC is less than KC, that's probably a better way to say it. If QC is less than KC, it means that you underdid it. You don't have enough products, right? You have too much reactants and not enough products. So how are you going to approach equilibrium? Some of the reactants are going to go to the right. This top arrow is going to beat out the bottom arrow for a little while until it gets back in equilibrium. Okay? So you're going to get there by shifting to the right. So I can make an overarching arrow. These guys have got to go that way out of the gate. Then it's going to come to equilibrium, and then it'll just stay there. Okay? So let's read this. QC less than KC, the reaction will shift to the right towards the products. Okay? What happens if you put in the concentration of C, square it, the concentration of A that you start with, the concentration of B that you start with, and this number over here is much, much bigger than the value that you look up in the book, whatever the equilibrium constant is. That means you overdid it. You have too much products. Your number is too big. So the only way to make that number smaller is for the numerator to go down and the denominator to go up. The numerator goes down and the denominator goes up, then that number will slowly go down, QC, until you reach equilibrium, and at that point, both arrows will be back equal to each other. Okay? So that's page 11 of the notes. Here comes page 12, the one we already discussed. If you happen to hit it, QC is equal to KC, the reaction is already at equilibrium. Okay? The next thing that we're going to work on is calculating what the equilibrium concentrations are given a scenario where a scientist does a particular experiment. So what I have here are a series of 2, 3, 4 different examples that we're going to go through that make for great practice questions for the test. Okay? So these are going to be calculating equilibrium concentrations. Okay, so first example. A gaseous mixture contains 0.3 moles of carbon monoxide, 0.1 moles of hydrogen, and 0.02 moles of water vapor at equilibrium. Okay, so this is a gas phase mixture, so this is water vapor over here. Plus an unknown amount of methane in each liter. Okay, the mixture at equilibrium, the mixture is already at equilibrium at 1200 Kelvin. If the Kc, you look it up, right? The Kc for this reaction is 3.92. What's the equilibrium concentration of methane in the mixture? Okay, so the first thing that you have to realize is, how big is my reaction vessel, right? Turns out that they made it an easy problem because the reaction vessel is exactly 1 liter. So if I think about it, right, it says I have that much in each 1 liter. So these numbers really are concentrations of molarity already, and they're equilibrium concentrations because it says it's already at equilibrium. Okay? All right, so first thing we should do is write down the equilibrium constant expression. So the equilibrium constant expression is, I have to give you the balanced equation. Carbon monoxide gas reacts with 3 molecules of hydrogen to create methane and water. The equilibrium constant expression, the equilibrium reaction has got to be balanced. So let's make sure it's balanced. There's 1 O over here. There's only 1 O in the water. Okay? All right. How many carbons? 1 carbon, 1 carbon. How many hydrogens? There are 6 hydrogens in the hydrogens over here. There's 4 in the methane, and 2 in the water is 6. So that's good. Okay. How do I write an equilibrium constant expression? The equilibrium constant at a particular temperature, in our case, 1200 degrees Kelvin, is equal to the products. Divided by the reactants, the coefficients become the exponents. These two guys are to the first power, this one's to the first power, and this one is to the third power. Everybody see that? Okay, next thing. From the problem, right, since it's a 1 liter vessel, the concentration of CO is 0.3. That was given to you. It's telling you the equilibrium amount. Usually, they're not going to be this easy. The concentration of hydrogen is 0.1. The concentration of water vapor is 0.2, and I don't know the methane. Well, look, I know the equilibrium constant expression follows this pattern. I know the equilibrium constant is 3.92. I know that value. I have this number, I have this number, and I have this number. So the only thing I don't have is the methane concentration. So how do I get the methane concentration? Just do algebra here, solve for methane. Methane is in the numerator, so I'm going to get Kc times carbon monoxide, that's going to come into the numerator, times the hydrogen to the third power is going to come into the numerator, all divided by the water vapor. Everybody see that? Cross multiply. These two guys come up here. This one comes underneath. You have no additive terms, so you can just cross multiply. Good? So algebra from here to here. Okay, what is the methane concentration at equilibrium? Just plug all the values in that you have from over here, solve for methane, and there you have it. Okay? Since it's a 1 liter vessel, that also gives you the moles. But in actuality, we're going to be interested in the molarity. Okay, just what is the concentration? So now you have all 4 concentrations at equilibrium. If you plug this back in up here, you better get 3.92. So that could be your check. Okay, let's talk about significant digits. These guys all had just 2 significant digits, so the methane should only have 2 significant digits. Okay. Concentration times volume, this is moles per liter times 1 liter, gives you the number of moles. Okay, so these guys are all bouncing around, reacting with each other. Once it comes to equilibrium, those are my 1, 2, 3, 4 values. Good. First example. Okay, here's example number 2. In this example, carbon monoxide reacts with water to make carbon dioxide and hydrogen. Okay? The Kc is given to you. Now remember, the equilibrium constant is only a function of temperature, right? If I throw this and this in, they'll come to equilibrium. You'll always get to 0.58. It's always going to be 0.58. The only way it's going to change from 0.58 is if I change the temperature. I'm not doing that. I'm going to do the whole thing at 1,000 degrees. Okay, so if you start with 1 mole of each carbon monoxide and water in a 500 milliliter vessel, how many moles of each substance will be in the equilibrium mixture at 1,000 degrees? Okay, so the first thing you realize is they did not give me equilibrium concentrations. They gave me initial concentrations. And they gave me just this guy and this guy. Okay, it's a free country. So they chose to put carbon monoxide and water into the vessel. Those two things have the ability to react using the top reaction to make some carbon dioxide and hydrogen. After some carbon dioxide and hydrogen build up, they can now hit each other and go backwards. Eventually, the beginning, only the forward reaction can happen. Once the products build up, the back reaction will slowly creep up with it, and eventually it will come to equilibrium when the 2 arrows are equal and opposite. The rate of the forward reaction will be tied with the rate of the back reaction. Remember, secretly, that's what the equilibrium constant is, when those two things come to equilibrium. Okay, so what do we need? We need to figure out our initial concentrations of everything that we have. Okay, all right, here's my reaction vessel. I can pretend it's a big cube, and inside my big cube, remember these are gases, right? So they're all trapped inside this big cube. My cube is only a half a liter. So if I want concentration, I have to take the number of moles, which they gave me, I had 1 mole of each, and divide by the volume. So my initial concentration of carbon monoxide is 1 mole divided by 0.5 gives me 2.0. That's my concentration, 2.0. Okay, a little hard to see that. Can you guys, how's that? You can see that now? I don't want to overdo it with the light. That's probably better. Good? All right, what's my initial concentration of water vapor? Remember, all gases, so it's water vapor. I also have 1 mole in 0.5 liters, so my initial concentration, I'm very careful not to use brackets. Brackets is going to be reserved for the concentration of things at equilibrium. So this is an initial concentration, so I even put a little 0 so you realize that before any chemistry starts to happen. Okay, 1 mole divided by 0.5 also gives me 2 molar, 2.0. How much carbon dioxide do I have at the beginning? None. Not because it can't be there, because the scientists didn't put any in. They just put 1 mole of this and 1 mole of that in my half-liter vessel and let it to come to equilibrium from the left. Okay? So this guy is 0 and this guy is 0 because they're not up here. Okay? All right. I have to do something called an ice table now that you may remember. So an ice table, you're interested in the I is for initial, the C is for change, and the E is for equilibrium. Okay? So I need to follow that. Now, in my ice table, it's very important that I list all of my concentrations in molarity. Don't do it in moles. You need to make the ice table in moles per liter. So here we are. We're in the right unit. This guy's 2, this guy's 2, this guy's 0, and this guy's 0. So those are the initial concentrations that I just calculated. Okay, so that's all we have so far. Okay, now we go back up to the top and ask ourselves what's going to happen. Well, we don't know how far this reaction is going to go to the right. Okay, we know the equilibrium constant, so I need to put in a placeholder for my stoichiometry, and my placeholder is going to be x, right? And then I'm going to solve for x. So x, since we know it's going from left to right, because I only have these reactants, I don't have any product, nothing can't react with nothing, right? You need molecules to react. So this concentration and this concentration have to go down. So I'm going to define x as the amount of carbon monoxide that reacts from the initial concentration. So I know the initial amount. I'm going to make the change equal to x. Okay, so x is our change. Now, based on the stoichiometry, I have to be careful. If this guy is going to go down by x, this guy's also going to go down by xy, because for every one of these that reacts, one of these also reacts. So how much does it change? This guy goes down by x, this guy goes down by x. Okay, let's look at the products. This one over here is going to go up by x and up by x, so they have positives. In this change column, the reactants will always be negative, the products will be positive. They don't always have to be x. Sometimes they could be a number if you know that number, right? Sometimes they can be 2x or 3x. Why would that be? Because the coefficients were different. If this guy had a 2 in front of it, for every 1 carbon monoxide that reacted, I would create 2 hydrogens. So over here, I'd have to call that 2x. So we'll see some like that. Okay. If I know how much I have to start with, and I know how much it changes, the equilibrium entry in this row is very easy. I just add these two things up. So what is 2 plus, right? Just sum them up is a better way to say it. What's 2 minus x? What happens when I put 2 and minus x together? When I sum up 2 and minus x? Well, I get 2 minus x. I had 2 to start with. We know it has to go down. We don't know how much yet, but it's definitely got to go down. That's what we're going to figure out. So our placeholder is x, how much it's going to go down. How about the water? Well, the water starts out at 2. It also goes down by x. I didn't have any carbon dioxide or hydrogen. So what's 0 plus x? 0 plus x is x, and 0 plus x is x. So here's my 4 equilibrium values. So what do I do with them? If they're equilibrium values, I'm allowed to plug them back into Kc. Okay, let me just make this a little bit bigger for a second. Excuse me. Here's my equilibrium expression. If I wanted to write it, Kc is going to be products divided by reactants. All the coefficients are 1. So here it is, right? The products divided by the reactants. So now, take that equilibrium line, guys, and just plug them in here. This one is 2 minus x. This one is 2 minus x. This one is, this one is x. This one is x. This one is 2 minus x. And this one is 2 minus x. So there I go. So what do? X times x is x squared. 2 minus x times 2 minus x is 2 minus x squared. So what I have here is a perfect square, right? The top and the bottom are both squared. So how am I going to figure out what x is? Right now, I have Kc is equal to x divided by 2 minus x squared. So I get rid of the squared by taking the square root of both sides. So that's what I have next, right? So that's just algebra. Take the square root of that. Okay, the square root of the value that they gave me, the square root of 0.58. Sorry about that, guys. I just lost my screen for a second. Okay, we're back. Okay, the square root of 0.58 turns out to be 0.76. Okay, so right here, I have everything that I had back up here, only I got rid of this squared by taking the square root of kc, but I just rewrote it on the left-hand side. So see that everything inside there is over here. Okay, so I take the square root of 0.58, I get 0.76. Now this is not a quadratic equation. There's nothing to be afraid of. This is a linear equation. So the next step that I need to do is just gather like terms. So bring this 2 minus x up here, right? And then multiply through. So what's 2 times 0.76? 1.52. And what's minus x times 0.76? Minus 0.76x. Okay, so right here, that's my whole equation. This is going to allow me to solve for x. And then once I know what x is, I can plug it back into here and get the equilibrium concentrations of everything that I have. This whole thing is going to go down from 2. It's going to go down from 2. These things are going to go up. Can't go down by more than 2 because you can't create a negative concentration of a material. Concentrations are amount of stuff, right? We don't have antimatter. So in this portion of chemistry, right? So I know x is bound, right? It can't be bigger than 2. It can get close to 2, but it can't be bigger than 2. Only the change columns can be positive or negative. And the cool thing, last thing I'll say is the change columns is they follow the stoichiometry. 1 to 1 to 1 to 1. 1 to 1 to 1 to 1. 2 going down, 2 going up. Good? 2 going down, 2 going up, all 1-to-1 relationships. Okay, how do I do the algebra on the next step? That's going to be on the next page. Very simple. Right? The next thing I do, let me go back over here, put them together. Okay, gather like terms. This term is a term in x. This term is a term in x, right? So I'm going to get them on the same side. Let's move this 0.76 over to make it positive. So I'm going to get x plus 0.76x is equal to 0.52, okay? So x plus 0.76x is 1.76x, and that's equal to 0.52. So algebra, algebra, algebra. Okay, last step. I'm not interested in how big 1.76 times x is. I want x by itself, so divide both sides by 1.76. 1.52 divided by 1.76 gives you an x of 0.89. Okay, last thing, go back into the equilibrium constant expression, or go back into the ICE table, find the equilibrium constants, and calculate what their answers are. So I'll put the two together, right? Like this. So how am I going to get this 0.86? I just figured out that x is 0.86, but x is the concentration of carbon dioxide. So that's an easy one. X is the concentration of hydrogen. Look, X is the concentration at equilibrium of hydrogen. Right? Look where that guy is. So that's 0.76. What's the concentration of equilibrium of carbon monoxide? 2 minus X. So 2 minus 0.86 gives me 1.14. What's the concentration at equilibrium of water vapor? 2 minus 0.86 gives me 1.14. Okay, so those are the 4 equilibrium concentrations. 1, 2, 3, 4. If anybody asked you how many moles you have, okay, the number of moles is going to be the molarity times the liters, right? Because what's the definition of molarity? Molarity is moles per liter. So anytime I want to know how many moles I have, I can just cross multiply. And moles is equal to molarity times liter. Remember, how big was my vessel? My vessel, at the beginning of the question, was just half a liter. So 0.5 liters. So if it's 0.5 liters, I have to take each one of these concentrations times 0.5, so they're all going to get cut in half, right? 0.86 divided by 2 is 0.43. Same thing with hydrogen. 1.14 is 0.57. 1.14 is 0.57. So in here, these are the moles. Honestly, on the test, we'll probably just stop with concentration. Concentration is really the important thing, okay? All right, the next example, now that was an easy one because you wound up with this perfect square, right? This guy, the top and the bottom are both squared. That's usually not going to happen, okay? Usually, you're going to wind up with a quadratic, and there's a simplification so that you don't have to do the quadratic equation, okay? So once in a while, we'll go ahead and do it, and I did it in this example, but later on you'll see, especially in test questions, they're going to simplify, okay? So let's take a look at example number 3. Make this a little bigger. Okay, so this is the one example that I'm not going to do our simplification with, so you see it one time. If you ever want to just use the quadratic and not do the simplification, you always can. There's never going to get the wrong answer. Okay, so example number 3. The equilibrium is the equilibrium between hydrogen and iodine to make HI, or hydrogen iodide. Okay, all in the gas phase, so there's nothing to leave out. Let's read the question. If 1 mole of hydrogen and 2 moles of iodine are placed in a 1 liter vessel, how many moles of each substance are in the vessel when it comes to equilibrium at 458 degrees C? Okay, the Kc is 458 degrees. The Kc at 458 degrees is 49.7. So our whole question is going to be at this temperature. So at this temperature, this will always hold. All right. First step, we can either write the equilibrium constant expression. It's going to be concentration of this at equilibrium squared divided by this to the first power divided by this to the first power, right? That's the equilibrium constant expression. That you can do right away. Okay. Second thing, what is the initial concentrations of everything? Well, we just have to be careful. How big is our vessel? Well, we're very lucky. Our vessel is exactly 1 liter, so if I have 1 mole of something in 1 liter, it's going to have a concentration of 1 molar. So that's what happens with hydrogen. Iodine is going to be 2, because 2 divided by 1 liter is going to give you 2 molar. So that's what I did here, right? The molarity is just the moles in 1 liter. I have a 1 liter, so my number of moles turns out to be also the concentration. What concentration? The initial concentration. Okay? How much HI do I have? Initially none. Not because I couldn't have put it in, but because I didn't. So this scientist chose to just put this and this together. Chemistry will happen if you have this and this together. You don't need any of this because the top reaction can happen right away. Then this will build up. Then they'll start to hit each other and go back to the starting materials. At some point, it will come to equilibrium. Good. All right, let's do our ice table. I is the initial concentration. C is the change. E is the equilibrium concentration. The ice table has got to be in moles per liter. Molarity, molarity, molarity. Has to be in molarity, not moles. Okay? This case, moles was the same as molarity. If it isn't, make sure you get to molarity. Okay. Well, these numbers we have, we purposefully put, the scientists put 1 mole per liter of hydrogen in, 1 mole per liter, 2 moles per liter of iodine in, and they did not put any HI in, so that concentration is 0. So those numbers, those initial concentrations, that's what the little 0 means, initial, go here. All right, next, ask yourself the question. When it changes, which way does it change? Well, only the top reaction can happen out of the gate. So whatever initial moles per liter I have of this and this, they have to go down because when it comes to equilibrium, the back reaction will start to catch back up, but won't go all the way back to the initial, right? The initial having some of this and some of this, right? If I plug that into here, this guy is 0, I'm not equal to Kc yet, right? The only way to get to Kc is for the denominator to go down and the numerator to go up until it reaches 49.7. So we're approaching the equilibrium from the left-hand side. Only the top arrow can occur initially. That's why X's for the reactants are going to be negative and X for the product is going to be positive. Okay, next thing. For every H2 that reacts, okay, I start with 1 molar and I'm saying by definition, or I'm saying I'm going to make X the amount of H2 that goes down. Well, if X is the amount of H2 that goes down, the amount of I2 goes down equally, because for every one of these molecules that react, one of these molecules react. The stoichiometry is 1 to 1. They have to drop together at the same rate. That's why minus X and minus X. Why is this positive 2X? Because for every one of these that goes down, I form 2 of these. So this is forming while this is going down. Minus X plus 2X. That relationship holds over here. This guy is going down by X. This guy is going up by twice as much. Okay? That middle row has got to follow the stoichiometry. 1 to 1 to 2. 1 to 1 to 2. Reactants going down, products going up. These numbers could be anything because it's a free country. The scientists could put anything they want inside the vial. Okay? You could start with 50 pounds of this, okay? As much as that physically can fit into the chamber, and just a little tiny bit of this, it's still going to come to 14.9. Always has to come from this side. The only way it can come from the other side is if you put a lot of this stuff in and a little bit of that. Then it might start out of the gate that way, okay? But since this is 0, you know you have to fill in the 0. It has to go towards the 0. That's why these are definitely going down. Okay, last one is very easy. How do I get the equilibrium? I just take initial and change and put them together. So 1 minus X gives you 1 minus X. 2 minus X, 2 minus X. 0 plus 2X is 2X. What do I do with the equilibrium concentrations? I just plug them into the equilibrium constant expression. This is the product, 2X. 2X goes in here, into this box here, and it gets squared. So it looks like you're double dipping. You don't just multiply it by 2, you also square it. What about the bottom? This one is 1 minus X. This one is 2 minus X. So they're not the same number, so I can't just take the whole thing and say squared and make this whole thing squared like the last one. This is a more realistic example. All right, so when I do this, I have this number, it's 49.7. I have a quadratic equation and we're going to do the algebra for it. What do we have to do? We have to solve for X. That's the first step. And the second step is going to be plug back into here, once I know what X is, to find out the equilibrium concentration of all the reactants and products. Good? Okay, that's 14. Okay, here's 15. Everything on this page is just algebra. So here's what I had from the page before, right? Nothing changed. 49.7 is the equilibrium constant that was given to me, right? And I plugged all those numbers, so I just put the 49.7 in. You can hand this over to your math teacher now. What did I do with the bottom? Well, you could do this 2 ways. This is probably the best way to do it. Excuse me, let me go back to here for a second. Okay. First thing I do is I square the top here. So that's okay because there's nothing added together. So what is 2x squared? It's just going to be 2x whole quantity squared is just going to be 4x squared, right? Then I have to multiply these two things in the denominator, which is a little bit more work. So that happens there. Okay, I'm going to just FOIL this, right? So first times first. 1 times 2 gives me 2. Outer times outer. 1 times minus x gives me minus x. Inner times inner. 2 times minus x gives me minus 2x. And then the last, negative x and negative x gives me positive x squared. Negative times negative is a positive. X times x is x squared. Okay, next step. When I get over here, I have some like terms, right? So I can put them together. This is a term in x here, right? This is minus, right? Looks like. Make sure we get that right. Good. This is a term in x, so I have minus x and minus 2x, right? I owe you an apple and I owe you 2 apples, so total, I owe you 3 apples. So minus x and a minus 2x is a minus 3x, okay? All right, last step. So I can get it to look like a quadratic equation. So I have this, right? Divide both sides, okay? So I just take this whole term over here, bring it up there, and bring the 49.7 underneath. So I'm just cross multiplying. This, everything in the denominator now is just going to come up here, and the 49.7 is going to go underneath it, right? So what do I have here? This is all of that now in the numerator, and the 49.7 is down there. Okay, you can do the math on this. This is 4 divided by 49.7. 4 divided by 49.7 gives you very close to 0.08. Okay, do it yourself. Times x squared. That's the x squared term. Okay, then I have over here is equal to 2 minus 3x plus 2x. So last step, gather like terms again. This is a term in x squared. This is a term in x squared, right? So I'm going to bring them both over to, let's actually bring everything over to this side, right? So I have x squared minus 0.080 x squared minus 0.08 x squared minus 3x plus 2 equals 0, because if I subtract 0.080 x squared from both sides, that's how I get a 0 over here. So once I get to this step here, this looks like a quadratic equation, right? So I have my coefficient of A, my coefficient of B, and my, when I get down to here, so this minus this, 1 minus 0.08 gives me 0.92 x squared. So this is my coefficient of A in the quadratic, minus 3 is B, and 2 is C, okay? So you know, whenever you have the quadratic set up like this, here's my relationship for the quadratic. So that's the coefficient A, that's B, and that's C. So the quadratic equation says x is going to be equal to minus the coefficient of B, which is negative 3, plus or minus the square root of the coefficient of B squared, so negative 3 squared, minus 4 times A times C. Here's A, here's C. Okay? Close this parentheses down here, all divided by 2A. So 2 times A, 0.92. Okay? All right, when I do this math here, what you're going to get is x is going to be equal to 1.63, okay, that's this part over here, okay, plus or minus 0.7. So you say, which one can it be? Well, two things you know about concentration. They cannot be more, well, right? They cannot be more than what you originally started with. So if I do the plus version, that's mathematically important, but physically, it makes no sense at all. So that's the one that you get rid of. So when I add it on, I get 2.33. When I subtract the 0.7, 1.63 minus 0.7 gives me 0.93. So I have two answers. Which is the one that is physically important in chemistry? Well, the one that makes sense. And I'll go back to here, the one that makes sense in terms of the stoichiometry. How can I subtract 2.33 from 1? Concentrations can never go negative, right? I have stuff. Concentration is amount of material. The lowest they can ever go to is 0. So if x works out to 2.33, x cannot be bigger than the thing that you're subtracting it from, okay? Doesn't even work out in this one. It doesn't work out in either one. So I throw this one out. It's physically impossible, and x has to be 0.93. the negative root, the root in which I subtract. Okay, if x is 0.93, let's go back and plug it in. Okay, let me show you the equilibrium. The equilibrium is here, right? So this is what, let me put these two things together. So what I'm going to get is the concentration of hydrogen is going to be 1 minus 0.93, because x is 0.93, okay? So that's going to give me 0.07. Just get the right page. This is 14. I could put this on the side. Okay, so 1, right, this was from the first page. The hydrogen is 1 minus x. We know x is 0.93, gives me 0.07. Okay, what is the equilibrium concentration of iodine? 2 minus x. So 2 minus 0.93 gives me 1.07. What's the concentration of hydrogen iodide? 2x. Where do I get that from? From right here. 2x. So this one, let me just get this like this for a second. So I plug back, my value of x is 0.93. I plug it back into these numbers, the equilibrium numbers. This one, now it's not just 1 minus x. I know this one is 0.07. I know this one is 1.07. And 2 times 0.93 is 1.86. So I have now, this goes here, this goes here, and this goes here. Okay? So those are my equilibrium constants. Now, I might be done. If they're just asking you for concentrations, those are the equilibrium concentrations. If it turns out that they're asking you for the moles, the last thing you have to do is go back and multiply by the volume of the vessel. Okay, so we'll go back and check that in a second. Okay, and I'll do that right now. Turns out we had a 1 liter vessel. So not only are these concentrations, these are also the number of moles, because molarity times 1 liter would give you moles. Okay, all right, so the last thing that I did, let me just get this back in order. The last thing that I did over here was just check, right? It's hard when you do a quadratic. That was a heck of a lot of math, and it was also like a lot of places where the significant digits can go awry, okay? So let's take our values and see how close we came, right? So turns out, well, we did get a little bit of a rounding error. If I take my answers and plug them back into the equilibrium constant expression, it should be the product squared divided by the 2 reactants. So I put all that stuff in, I get 46.2. We started with 49.2. What's the 3 difference? That's just a rounding error, so don't worry about it, okay? All right, so since the flask was 1 liter, the moles are equal to going to be the molarity times the 1 liter. So the numbers here are going to be exactly the same as the numbers here. Let me just make this a little smaller, all right? Because the moles are going to be equal to the molarity. But again, in the test, I'm more interested in just getting to the concentration point, right? Concentration is going to be really important for us the rest of the class. We're not usually interested in moles. Okay? Who cares how big the liter, the vessel is? We want to know what the concentration is. Good? All right, so that's among the harder ones that you're going to see, because you actually have to do the quadratic. There's no way around the quadratic because the equilibrium constant was high, and this went pretty far to the right, so x was a substantial number. Look, x as compared to the number that you're subtracting it with, it's substantial, right? It's most of it. So you can't just drop the x on the reactants like we're going to do in some cases going forward. Okay, and we'll wait to talk about that. Okay, let's look at our fourth example. And actually, this is our last example. This is equilibrium constant in terms of concentration again, as opposed to equilibrium constant in terms of pressure, Kp. So let's take a look at it. So we're saying that phosphorus pentachloride reacts, decomposes to give us phosphorus trichloride and chlorine gas. the Kc is given to us at 25 degrees. It has a Kc of 1.3 times 10 to the minus 5 molar. So this is only going a little bit of the way to the right. Most of it stays as phosphorus pentachloride. How do I know that? Because Kc is the products divided by the reactants. The coefficients become the exponents. So it's this times this divided by this. Well, this times this divided by this at equilibrium is always going to be 1.3 times 10 to the minus 5. That's tiny. That means these concentrations are very low. Okay, let's look at our example. So we know that if I only start out with phosphorus pentachloride, which I'm going to in this case, has to go to the right, but it's only going to go to the right a little bit because my equilibrium constant is so small. So let's see what it says. It says if 2.0 molar phosphorus pentachloride is allowed to come to equilibrium at 25 degrees, what is the equilibrium constant expression of each of the species? Well, they gave me this in concentration. I've got 2 molar, so I can go right to my ice table. I don't have to worry about moles. It's already in molarity, and we know ice tables have to be in molarity, molarity, molarity. They won't work in moles, okay? Unless it just happens to be that all of the molarities are the same number as the moles, okay? Be careful though. Molarity, molarity, molarity. All right, so write down our species. Here's the balanced equation. Phosphorus pentachloride decomposes to give you phosphorus trichloride and chlorine. Okay, the scientist, she chose to put 2.0 moles per liter of PCl5 into the vessel. Has to go to the right initially. How can the back reaction possibly happen if I don't have any of this and this? Okay, if she would have thrown this and this in, it still has to go to the right because even if just one of them is 0, how can this possibly react? The only one that can react is PCl5 because it is just a decomposition. These guys are a PCl5, it must be smashing into another PCl5 to break apart to give you this and this. Okay, so only the top arrow can occur out of the gate. The top arrow is going to start out, PCl5 is going to drop. These two products are going to start to grow in to the point where they now can turn around and react with each other. The back reaction is going to creep up on the top reaction until they get to equal and opposite. That's what equilibrium is. So we're approaching equilibrium from the left-hand side. So when I approach equilibrium from the left-hand side, I have this. I'm going to make my x equal to the amount. I get to choose what x is. The easiest thing to make it is let x be the amount of PCl5 that reacts in moles per liter. Okay? So if that guy goes down by x, there's no other reactant, this guy is going to grow in by x, and so is this, right? Because the coefficients are 1. So they're positive because they are products. This one is negative because it's a reactant. And their coefficients are 1 because the stoichiometry is 1 to 1 to 1. 1 to 1 to 1. What did I tell you about that middle row? That middle row will be exactly always stoichiometrically equivalent to what's up here. 1 to 1 to 1. In our last example, it was like 1 to 2 to 1 or something. Okay? Good. So if I have 2, and this goes down by x, it's 2 minus x. This is 0 plus x is x. This is 0 plus x is x. So here, these are the equilibrium concentrations. Plug them into the equilibrium constant expression. It's the products divided by the reactants. So what I'm going to get is x times x in the numerator, which is x squared. Okay, I never wrote down the equilibrium constant expression, but I can quickly. Kc is equal to PCl3 times Cl2 all divided by PCl5, right? That's the equilibrium concentration. So this is x, this is x, this is 2 minus x. All of that comes from here, right? Go back and plug those into here. Plug the equilibrium constant expressions into the equilibrium, plug the equilibrium concentrations into the equilibrium constant expression. X gives you x squared, x. and this is just 2 minus x. Okay, now when I get this, right, when I get this, I would have to do a quadratic if I just left the x in over here. But let's take a look at KC. Since KC is so small, so much smaller than what you're starting with, it's going to be okay to drop the x because the 2 is going to be enormous next to x, and we'll see that when we're at the end. Okay? I can't drop the x here and here because that's the only thing I have, and they're going to be multiplied by something. But when I have an x that's subtracted or added to a number that's much bigger than it, this is like saying I've got $2 million and x is 50 cents. If somebody had $2 million, they don't even bother counting the 50 cents to subtract it off or add it. Okay? So you just can drop the x from something when x is added or subtracted to a number that's much bigger than it. Again, how do I know x is going to be small? X is going to be very small because the equilibrium constant is small. Okay? So what you're looking for to know that it's okay to drop the x is you're looking for 100-fold difference. Okay? 10 to the 2 difference between the number that you're subtracting x from and the equilibrium constant. Well, this guy is 2, that's first order. This is minus 5, right? So this guy is 5 orders of magnitude smaller, 10 to the 5th times smaller than 2. Okay? If this was 0.2 instead of 2, which a lot of times it is going to be something like that, this is 0.2, then now it would be 10 to the minus 1, this would be 10 to the minus 5. It would be 4 orders of magnitude, but I could still drop the x because that's 4 orders of magnitude. All I really need is 2 orders of magnitude different, 100-fold different, and then it's less than 1%. Okay? Sometimes people use the 5% rule. If x is less than 5% the number you're subtracting of, oh, who cares, just drop it. $95 is good, close enough to 100. Right? $105 is close enough to 100. So you go to a flea market, you're bargaining with the person, and they want $105 for the table, and you only want to give them 100. Come on, you're going to make a deal over that. You're going to say, oh, I don't care. The x, the little difference, is not much next to it. Okay? So 5% is one way to look at it. I even think you can just use 1% a lot of times. 1%, it's even being more conservative. 1% would be 2 orders of magnitude between this number and this number. That means this could have been as big as 10 to the minus 2, and I could still drop the x. So there's no question x is going to be teeny, and we'll see that in a second. Okay, so if I drop the x, look what's going to happen, how easy this is going to be. I'm going to have kc is equal to x squared divided by 2. It's going to be okay to drop the x. Okay, so what does it say down here? This is approximately 2. It's going to be 1.99 something because x is so much less than 2. Okay, let's see. If I drop the x then, look how simple my equation is. Okay, first thing I do, I have the value of kc. I'm sorry I didn't write it. I'll go show you where this, oh, I'm sorry, I have it over here. So kc is 1.3 times 10 to the minus 5, so I plug that in there. So I got 1.3 times 10 to the minus 5. This was given at that temperature. That's the equilibrium constant. So I just now have to take this very simple equation and solve it for x. So first thing, take my 2 in the denominator and cross multiply it. Next thing, I'm not interested in x squared. I'm interested in x. 2 times 1.3 times 10 to the minus 5 is 2.6 times 10 to the minus 5. Last thing, take the square root of that number to get x. So what have I figured out? X is 0.0051. Wow, is that less than 2? Yes. So it was okay to justify dropping the x because this is way less than 1%. Okay? Nowhere near it. You're going to see how small it is in a second. Okay? So I'm dropping this. So 2 minus this number is so close it doesn't matter. Okay, so what is the concentration of PCl3? Well, go back. Concentration of PCl3 is X, right? So we need that. Put this on top of here. I just figured out that X is 0.051. So that's the concentration of PCl3. It's also the concentration of chlorine because the concentration of chlorine is X. The concentration of PCl5 is basically 2, right? Because 2 minus 0.0051 is 1.99549, right? Let's see what it is, and you'll see that that's such a small number, right? So you see how small it is. If I subtract it or I don't, it makes no difference, right? So 2, it's not significant, right? That's the whole idea of significant digits. You would just round this up to 2 anyway. So 2 minus 0.0051. Ooh, I added it, sorry. 2 minus 0.00051 equals 1.9949. Come on, that's 2. So to the number of significant digits that we're doing this, it didn't matter if I subtracted it or not. It's basically 2, so don't even bother subtracting it over here. That number is 2. Okay? 1.9949 is so close to 2, just round it to 2. Okay? All right, so those are your 3 equilibrium concentrations. That's here, in my make-believe box that I'll put around here, those are your answers. Okay? Maybe we'll make a real box, okay? Last thing, you can drop the X when it's less than 5% of the number. 1% of the number is 2 orders of magnitude less. So if you have 0.1 and your equilibrium constant is 10 to the minus 3, that's fine. That's 2 orders of magnitude less. If you have 0.01 for your initial concentration of something and you're going to subtract X, then you need 0.01 is 10 to the minus 2. So you need the equilibrium constant to be 10 to the minus 4. As long as you're 2 orders of magnitude, okay? And that's being even more conservative than this. Well, let's see. If it says you can drop the X when it's less than 5% of the number, how big is X compared to the number we were subtracting it from? Well, percent is the part over the total times 100. So 0.0051 divided by 2 times 100 gives us, we can go all the way up to 5%, and we're only at 0.26%. So it's definitely no-brainer, okay to drop. Okay, so that gets us through page 17 of the notes. We only have one more section to cover for chapter 15, and that's going to be Le Chatelier's principle, and we're going to do that in the next, which would be the last video for chapter 15. Thanks, guys. See you next time.